Thanks. Okay. Good afternoon, everyone. My name is Kaifeng Yang, a postdoc researcher at University of Applied Sciences of Austria. Today, my presentation is quantifying uncertainties of residuals in symbolic regression by using Kriging or Gaussian processes. This is the outline of my presentation today. First of all, I will briefly introduce the background and the motivation of this research. Then I will introduce two methods that build up the proposed algorithm. They are genetic programming based on symbolic regression and Kriging. Later, I will show you how the proposed algorithm works. At the end, I will show you some experimental results and conclude this work. As we all know, genetic programming based symbolic regression is a technique of using genetic programming to search for a closed-form mathematical expression that best fitted a data set. Since this approach built up the model in terms of a mathematical expression that is explainable to an expert, this strategy belongs to the white box modeling domain, and therefore it is widely used in industry. In an ideal case, we want our prediction model could be exactly the same with the real industry process or real model. But of course, we know that this is not possible in practice because of the prediction error or residue. A common way to solve this problem is to optimize the hyperparameters of the model by maximizing or minimizing some score function or loss function, like mean squared error, MSE, coefficient of determination, R2, and so forth. And now, let's think this question in another way. Since we cannot dimension the residues of the prediction, why not to build up an error model for this residue? A very straightforward idea is to use a hybrid model, where a mathematical expression is used to predict the outputs, and another corresponding model is used to predict the residue of the outputs of the symbolic expression. Actually, this is the motivation of this work, and also the basic idea of the proposed algorithm in this work. In an ideal case, this error model should predict not only a residue, but also the confidence or uncertainty of the residue, because this confidence of the residue is also very important, and we can play a lot of games on it. For example, we can use uncertainty as the second criteria to judge the quality of the residue and even calculate the expected residue. Now let's briefly see the related methods used in this work. In this work, we use the genetic programming, GP, to search for a mathematical expression that best fitted the data. GP is an evolutionary algorithm to solve an optimization problem. Similar to other state-of-the-art evolutionary algorithms, GP also involves a population of solution candidates by following Darwin's theory, survival of fittest. GP also utilized some biological inspired operators like mate selection, crossover, mutation, and so on. One thing that distinguishes GP from other evolutionary algorithms is the representation of a solution. In other evolutionary algorithms like evolution strategies, genetic algorithm, PSO, a presentation of solution X has a fixed length, but the GP has a variable length for solution X. So this feature allows GPs to search for any free-form structure in symbolic regression problems. The definition of GP-based symbolic regression is defined here. The search space of GP-based symbolic regression is a union of a function space, F, and a terminal space, T here. And here, a function space contains all the possible mathematical functions like plus, minus, log, and any other mathematical operators. A terminal space contains all the variable symbols like x1, x2 that exist in the data set, and also contains some real numbers. Then GP will construct a mathematical expression T by using the function operators in function space and the variable symbols and constants in the terminal space. Then the mathematical expression T will be evaluated by an objective function and then optimized by logically inspired operators in GP. Theoretically, any performance matrix can be used as the objective function in GP-based symbolic regression, like mean-squared error, normalized mean-squared error, Pearson correlation coefficient, PCC, R2, and etc. In this work, we use the PCC as the objective function in GP, as it ranges from -1 to 1, and there is no need to normalize it. Besides, PCC reflects the linear relationship between two samples and will not destroy the distribution property in the dataset. Now let's see another technique used in this work, that is Kriging. Kriging, also named as Gaussian processes in some papers, and it is a form of a Bayesian interface. Suppose that we have a dataset D, which contains decision vectors X and their corresponding outputs Y. Kriging starts with this dataset D. In Kriging, we assume that the dataset follows a normal distribution with parameters of mean and variance. Based on the dataset D, the posterior distribution can be estimated by using the maximum likelihood principle. Of course, this posterior distribution is also a Gaussian distribution. Then, given an unknown or target point xt, we can use this posterior distribution to estimate the output of the target point. The prediction itself also follows a normal distribution with parameters of a mean and variance, and this variance can also tell you the confidence of the mean. The basic idea of the proposed algorithm is very simple. That is to build up a hybrid model which contains two parts. The first part is to use GP-based symbolic regression to search for the best fitted symbolic expression. And then the second part is to use Kriging to build up the residue model for the first part. That is the symbolic regression, symbolic expression optimized by GP. This figure shows you the workflow of the proposed algorithm. First, given a dataset D, GP is firstly used to search for an optimal symbolic expression. Then, this optimal symbolic expression is evaluated on the dataset, and we can calculate the residues of this optimal expression over the dataset. Later, we will use Kriging to predict the residues. Then the next question is, what kind of factors affect the residues? Or what are the decision vectors for Kriging? The residue is by nature determined by input X to symbolic expression. Another intuitive factor that affects the residue is the predictions of the symbolic expression Y hat. So the decision vectors to Kriging XGP can be set by three different ways. Input X to symbolic regression X, the prediction of the symbolic regression Y hat, and also the union of X and Y hat. The final model of the proposed algorithm is the sum of the symbolic expression and the Kriging model for the residue. In this work, we use the GP squared to represent the proposed algorithm. To distinguish the three different strategies of setting XGP, we use GP squared 1 and the GP squared 3 to represent the setting decision factors X, GP as Y hat and X respectively. Besides, GP squared 2 stands for the strategy of using the union of X and the Y hat to predict the residues. We tested the proposed algorithm on three variants with the GP-based symbolic regression and the Kriging on three state-of-the-art problems. They are polyton, fragment 1, and fragment 2 problems. The size of the dataset D has 1,000 samples, while the first 70% samples are used for training and the remaining samples are used for test. We did 31 independent repetitions for each algorithm on a specific problem. The published size is 4,000 and the maximum iteration is 20 for all algorithms except for Kriging. Besides, we set another stopping criteria in GP, that is the maximum PCC value of the optimal symbolic expression, and we set maximum PCC value as 0.99. Now let's see the experimental results. This slide shows prediction performance of all the algorithms with respect to a common performance metric, mean squared error, and its standard deviation. From this table, we can clearly see that Kriging and GP squared yield the best results in a training dataset. This is reasonable because Kriging is an unbiased predictor. In the test dataset, the three variants of the proposed algorithms by using the Kriging to model the residues yield better results than GP and Kriging with respect to MSE. Among all the test algorithms, GP squared 1 yields the best result on all the test problems with respect to mean squared error and its standard deviation. This table is the well-consensus rank test at 5% significance level. The results show that GP squared 1 is significantly different from the other four algorithms. Considering the fact that the GP squared 1 has the smallest MSE on all the test problems, this table also confirms that the GP squared 1 is the best algorithm among all the test algorithms. This figure shows the prediction of GP Kriging and GP squared 1 on polyton problem. The left, middle, and the right figures show the result of GP-based symbolic regression, Kriging, and the GP squared 1 respectively. In all the figures, the red dots represents the array outputs in the dataset, while other colored dots represents the predictions. From this figure, we can easily see that the predictions by GP squared 1 is the best fitted to the dataset. Similar conclusions can also be found on fragment 1 and 2 problems. To conclude, in this work, we propose the GP-based symbolic regression with Kriging, and that is a GP squared compared to the GP-based symbolic regression. The built-out model of GP squared is a sum of symbolic expression and one additional residual term. In the model of the proposed algorithm, symbolic regression part can be used to explain the working mechanism of a complex system, and the residual term is used to regulate the predictions by predicting the residuals. Besides, the residual term also follows a Gaussian distribution. Therefore, we can also access its uncertainty or confidence of the predicted residuals. The experimental results show that the proposed algorithm works, and one of the three variants, GP squared 1, yields the best results among all the 5 algorithms with respect to mean squared error metric. For future work, it is recommended to test the proposed algorithms on some real-world applications and use the proposed algorithm as the circuit models in circuit assistant, single, and multi-objective optimization algorithms. Thanks for your attention.